There's a machine in California that must be kept colder than deep space itself. Not because it is dangerous, but because if the outside world interacts with it even slightly, the delicate quantum state inside begins to collapse. That is what makes this story so fascinating. Quantum artificial intelligence is not simply delivering faster computation. It is forcing us to confront one of the oldest questions in physics. What does reality do before it is observed? Inside a quantum computer, particles can exist in multiple possible states at the same time. But the moment information leaks into the surrounding environment, those possibilities collapse into a single definite outcome. Machines such as Google's Willow are transforming this mysterious behavior into practical technology. The deeper scientists explore quantum mechanics, the more it seems that the solid world around us may only be the visible surface of something far stranger beneath. At the heart of a quantum computer is not a massive engine, but a tiny chip containing qubits. Unlike the bits in a conventional computer, which can exist only as either 0 or 1, qubits can exist in a superposition of both states simultaneously. This extraordinary property is what gives quantum computers their immense potential. When many qubits become entangled, they can explore an enormous number of possibilities at once, far beyond what even the most powerful classical computers can realistically process. There's, however, one enormous challenge. Superposition is incredibly fragile. A tiny vibration, a stray photon, or even the slightest electromagnetic disturbance can destroy the quantum state. That is why these machines must be cooled to temperatures even colder than the space between galaxies. For a brief moment, the quantum computer creates a protected environment where the outside universe is almost prevented from interfering. Within that silence, the qubits can perform calculations while reality itself has not yet settled on a single answer. The mystery behind this behavior began long before quantum computers with one of the most famous experiments in physics, the double-slit experiment. It is one of the simplest experiments ever designed, yet also one of the most unsettling. When particles pass through two slits without anyone measuring which path they take, they create an interference pattern as though each particle somehow traveled through both slits simultaneously. However, when a detector is placed to determine which slit each particle passes through, the interference pattern disappears. The particle behaves as though it chose only one path all along. That is the unsettling detail. The difference is not caused by a collision or physical force, but by information itself. When the universe contains no record of the particle's path, it behaves like a wave of possibilities. Once that information exists, those possibilities collapse into a single outcome. This puzzle is known as the measurement problem. After nearly a century of research, physics can predict these outcomes with astonishing accuracy. Yet it still cannot fully explain why one definite reality emerges from countless possible ones. Albert Einstein believed that particles must possess definite properties even before they are measured. The idea that reality only becomes definite through observation seemed incomplete and deeply unsatisfying to him. Einstein argued that there had to be hidden information beneath quantum mechanics, a deeper layer explaining what particles were truly doing before anyone observed them. Later, physicist John Bell transformed that philosophical debate into a scientific test. If hidden variables really existed, particle behavior would have to obey specific mathematical limits. Quantum mechanics, however, predicted that entangled particles would violate those limits. When experiments were finally carried out, the universe consistently agreed with quantum mechanics. Time after time, entangled particles displayed correlations far too strong to fit Einstein's classical picture of reality. These results suggest that, at its deepest level, the universe is not constructed in the intuitive way our everyday experience would lead us to believe. This is why the mystery extends far beyond strange particles inside a laboratory. It implies that the familiar, solid world we experience every day may emerge from underlying rules that are neither solid nor intuitive at all. Google's Willow quantum processor has brought this decades-old mystery into the era of quantum artificial intelligence by demonstrating that these incredibly delicate quantum states are no longer just laboratory curiosities. They are becoming systems that engineers can reliably control on a meaningful scale. With 105 qubits, improved coherence, and significant advances in quantum error correction, Willow showed that quantum systems can actually become more stable as they grow, one of the major milestones on the path toward practical quantum computing. Perhaps the most remarkable achievement was its benchmark performance, completing in minutes a calculation that would require an unimaginably long time for a classical supercomputer. This accomplishment does not prove the existence of parallel universes, nor does it solve the measurement problem, but it makes those questions impossible to ignore. If a quantum computer truly uses superposition and entanglement to explore an immense landscape of possibilities simultaneously, then what is actually happening inside the machine while the computation takes place? The uncomfortable truth is that the mathematics works, the hardware works, and the predictions work with extraordinary precision, yet the deeper meaning behind them remains unresolved. That may be the most profound mystery that quantum artificial intelligence has revealed. We are beginning to build the technologies of the future upon a reality that we can manipulate with incredible accuracy, even though we still do not fully understand its true nature. Perhaps the strangest part of this story is that quantum behavior is not confined to advanced laboratories or hidden inside machines like Willow. The same quantum rules are operating at this very moment inside the atoms of your body, the air surrounding you, and the light passing through the room. Your hands feel solid because they are constantly interacting with everything around them: photons, air molecules, heat, nearby surfaces, vibrations, and countless other particles.